identify the compound with molecular formula C8-H10-O, which gives the following IR and a Nmr spectrum. Okay, when the molecular formula is given, the first thing that you would start on is to find the degree of unsaturation of the compound using the formula here. So 2C plus 2 plus nitrogen minus H minus hydrogen divided by 2. So using the formula, if you calculate it, it's going to be 2 times of 8 plus 2. There are no nitrogens, so it's going to be 0, no halogens, 0 again. And the number of hydrogens here is going to be 10, okay, and the whole thing divided by 2. So it's going to be total of 16 plus 2 minus 10 divided by 2. That's going to be equivalent to 8 by 2. It's going to be 4. Okay, so this compound has a total of 4 degrees of unsaturation. Now let's see whether we are able to find any information from the IR spectrum. So in the IR spectrum, if you drop a line right there around 3000, there are some peaks on the right side, which is going to correspond for the sp3 carbon hydrogen stretch. And there are some peaks on the left, which is going to correspond for the sp2 carbon hydrogen stretch. Again, when you look into this region right here, there are some peaks around it, and this peak around 1600 and 1500 is going to correspond for the benzene rings, the carbon-carbon stretch in the benzene ring. Okay, and apart from that, we also have 2 distinct peaks, one around 1200 and another one around 1020, and that's going to correspond for the carbon-oxygen bond. Okay, so the peak around 1200 is going to correspond to the carbon-oxygen, but it's going to have a partial double bond character. But the peak around 1020 or 1010 is going to correspond to the carbon-oxygen pure single bond. Okay, so these are the information that we could get from the IR spectrum. Now let's take a look at the NMR spectrum. From the NMR spectrum, it's very obvious that there are some aromatic protons, which accounts for a total of 2 plus 2 equivalent to 4 protons, and they appear as 2 doublets. So this pattern right here, when you see 2 doublets, which is equivalent to a total of 4 protons, is going to be consistent for a para-substituted benzene. So which is going to have this structure. So this is a 1,4 substituted or para-substituted benzene, where there are 2 groups in the 1 and the 4th position. One in the first position and the other one in the 4th position. Now let's look into the other region of the NMR. So here you have 2 peaks, only 2 peaks. So there are only 2 different types of protons, and these 2 different protons exhibit as 2 separate singlets, each accounting for 3 hydrogens. So in general, when you see a peak that corresponds to 3 hydrogens, it should normally be a methyl group. And you can clearly see from here that there is one methyl group which is in the upfield region, and there is one other methyl group which is in the far downfield region, about 3.8. So this is going to be, this peak around 3.8 is going to be for OCH3. When it is connected to an oxygen, when a methyl group is connected to an oxygen, then it's going to show a singlet around 3.8. Now the final thing that we have to do is put all of these information together that we have gathered from IR spectrum and NMR spectrum. We already know that there is a para-disubstituted benzene ring, which is going to be looking like this, right? And here is our OCH3 peak, and here is our CH3 peak. So we have those 2 groups. Okay, and we wanted to calculate all of these carbons, hydrogens, and oxygen and see whether this is consistent with our given molecular formula. For the para-disubstituted benzene ring, the molecular formula is going to be C6H4, since 2 of the hydrogens has been replaced by 2 substituents. Okay, and we have an oxygen from the OCH3 group, and when you calculate the total number of carbons and hydrogens here, it's going to be C2 and H6. So on the whole, it's going to be C8, H10, and 1 oxygen. So this is definitely consistent with the given formula, C8 with the given formula. So now we know that there are not going to be additional protons or any other additional groups. We just needed to put the 2 groups. We only have 2 groups, OCH3 and CH3, and we are just going to put the 2 groups in the para position, and this is going to be our final structure. This is going to be our structure that's consistent for the given molecular formula and the IR spectrum and the NMR spectrum.